Hello everybody, welcome to another video lesson. Today we're going to be talking about sum and difference identities of our trigonometric functions, okay? So our objective for this lesson, we're going to be able to use these sum and difference identities to evaluate our trigonometric functions, okay? So first thing, let's get into this. We're going to get into a proof of concept first, okay? So now I've got this unit circle diagram that we're going to be working off of here. Now I hope we can see I have this angle beta right here, okay, and I have this angle alpha right there. Okay, now what we're going to try to prove today is one of our sum and difference identities. We're going to prove the difference of cosines here. So we're going to try to prove and find out what cosine of alpha minus beta is equal to. Okay, cosine of alpha minus beta. Okay, so what we're going to do is I'm going to take a second unit circle here, and I'm going to rotate this triangle. Okay, I'm going to rotate it clockwise by beta degrees. Okay, so here I've got this this segment here. Okay, and I've rotated clockwise beta degrees, so that is now on my x-axis. Okay, and then my segment for this alpha angle, okay, my terminal side here, I've rotated beta degrees clockwise as well. So it's going to look something like this, okay? Now I hope we can see that by doing this, okay, I haven't changed the shape of this triangle here, okay? This chord CB is actually equal to this chord DA here, okay? Those are going to be the same length because I haven't changed anything about my triangle. All I've done is rotate it about the origin, okay? Again, by beta degrees. Okay, so what we're going to do, I'm going to use the fact that CB is equal to AD, okay? Again, that's CB, that's my orange chords here, is equal to AD, okay? Okay, and keep in mind, we're going to be using these XB and YB because these are the coordinates of our points here, okay? So at C, I've got XC, YC, and at D, I've got XD, YD, okay? And here at A, since this is a unit circle, this is just going to be 1, 0 here, okay, on my x-axis. So we're going to use our distance formula. We're going to use our distance formula first, and that's going to tell us that XB minus XC squared plus YB minus YC squared, that's going to be the length of my CB right here, okay? This CB is equal to the distance of that chord is equal to that formula right here, okay? And same with my AD, all right? I'm looking at this chord right here, okay? That's equal to XD minus my 1 here, okay, plus YD minus my 0. Okay, and I'm just getting that from the coordinates of my points here between my terminal side of my angles and my unit circle, okay? Okay, so since I have a square root on both sides, I can just square both sides and those will go away. Okay, and then I'm going to go ahead and I'm going to FOIL out each of these binomials, okay, each of these binomials. So I can see my orange binomial here is going to factor into xb squared minus 2xbxc plus xc squared, okay? And I've got similar expansions for my yb and yc terms, and similar expansions for xd and 1, okay? And then yd minus 0, that's a little bit easier. That's just going to simplify to yd squared, okay? Now, keep in mind, since I'm working with a unit circle here, okay, all these x's and y values are actually equal to cosines and sines, okay, of alpha and beta. Okay, look at this, xb, okay, that's equal to the cosine of beta here, right? And yb is equal to the sine of beta as well. Okay, and same with my alpha angles. Okay, so when I consider that, okay, if I take a look at xb squared, okay, if I have xb squared plus yb squared, well, that's the same as cosine squared plus sine squared, right? So that's going to simplify to just 1. Okay, so those guys will kind of go away because they simplified to just 1. And same thing with x xc squared and yc squared. Okay, when I add those two together, those just simplify to 1 because of our trigonometric IDs. I'm sorry, this should be a 1. 1. Okay, so I'm left with this minus 2. On my left-hand side, I'm left with minus 2xb xc minus 2yb yc. Okay, and that's equal to our right-hand side here. Okay, so I've got a similar simplification going on here. Okay, I've got xd squared and yd squared. Okay, so again, those simplify to just 1 because cosine squared plus sine squared is equal to 1. Okay, and then I've got a 1 here as well, so plus 1. And then I've got this negative 2xd. Okay, so I've simplified pretty good here. Okay, and I've got this 2 on this side and a 2 on this side, so those guys will cancel each other out. And then I've got a bunch of 2's as well, a bunch of negative 2's, okay, that we can factor out, and that will cancel each other out also, okay? So when I go ahead and I simplify all that, get rid of my arrows here and all this, okay, that's just going to leave us xb xc plus yb yc is equal to xd, okay? That is just simplifying straight from that distance formula, and everything that we just simplified further. Okay, we're going to be left with xb xc plus yb yc is equal to xd. Okay, now keep in mind again, since this is my unit circle, okay, all of these, okay, xb is equal to sine of beta, xc is equal to cosine of alpha, okay, or sorry, xb is cosine of beta, xc is cosine of alpha, and my y values are just sines of alpha and beta. Okay, so I can go ahead and use substitution, and I prove that cosine of alpha minus beta is equal to cosine of alpha times cosine of beta plus sine of alpha sine of beta. Okay, so that's one proof of concept there for one of our sum and difference identities. But we actually have 6, and we're not going to go ahead and prove all of them, so I'm just going to put them up on the screen here. Make sure you write these down because we are going to be using these extensively in the rest of the lesson. But for now, let's go on to example number 1, okay? How can we use these sum and difference identities here contextually, okay? Well, if we're asked to find the exact value of a trigonometric function that we don't really know, okay? We know, say, cosine of 30, right? And we know cosine of 45 and 60 degrees, okay? But cosine of 15, we don't really know, right? It's not on our unit circle. It's not something we can easily memorize, okay? So we're going to use our difference identity for cosine, okay? That says that cosine of x minus y is equal to, well, this is what we just proved, right? We just proved this. Okay, so I'm going to take this 15 and we're going to change this into cosine of 45 minus 30 degrees, okay? Because 45 minus 30, that's equal to this 15 here, right? It's the same thing. So we're allowed to do that. So now I've got cosine of 45, okay, times cosine of 30 plus sine of 45 times the sine of 30, okay? Okay, so, and then we can go ahead and simplify from there, right? So I know cosine of 45, that's going to be root 2 over 2. Okay, and cosine of 30, I know, is going to be root 3 over 2. Okay, so those guys are multiplied together. And I know sine of 45, again, is root 2 over 2. And sine of 30 is going to be 1/2. Okay, so this will go ahead and simplify further to root 6 over 4 plus root 2 over 4. Okay, and now I can get this exact answer if I combine this all under one fraction of root 6 plus root 2 over 4. Okay, root 6 plus root 2 over 4. So that would be the exact answer that I would be left with. Okay, and we couldn't find that before we had our sum and difference identities. Okay. Okay, moving on to example number 2. Okay, we can kind of work backwards on this one, all right? So I'm given this real long expression here, but I also know that this kind of looks like one of my identities, right? And in fact, it looks like this cosine of, or the difference identity for my cosine, right? Okay, so here I'm going to have 7 pi over 8. That's going to be my, think of that as x. Okay, and then our 5 pi over 24, we're going to think of that as our y, right? So this is cosine x cosine y plus sine x sine y, okay? Just like we have over here at with our with our identity, okay? So we can simplify this to just cosine x minus y. So cosine of x is 7 pi over 8 minus y, which is 5 pi over 24. Okay, so we can go ahead and simplify this to cosine. Okay, can have 7 pi over 8 is going to be 21 pi over 24. Okay, minus my 5 pi over 24. Okay, so this is going to equal cosine of 16 pi over 24, which further simplifies to cosine of 2 pi over 3, and if we have a look on our unit circle, we know that that is equal to 1/2, okay? Okay, so that would be our exact value, really simplifying this long expression here into something much simpler that we know how to define, okay? All right, taking a look at our third example. Okay, again, we're given this kind of ugly quotient here, okay, but this really just looks like the difference identity for our tangent, okay? Okay, so here I've got this 6x, that's kind of our 6x, that's our x here, okay? And then our 7x, that's our y, okay? That's our y. That's my y right here, right? Okay. So since the rest of this equation checks out, okay, we can simplify this to tangent of x minus y. So 6x minus 7x. Okay, so this is going to be tangent of negative x. And notice we're just asked to simplify here. Okay, just asked to simplify. So we might think we might be done, but we can actually simplify this further because tangent is an odd function, right? It has this odd characteristic to it. Okay, so that means that tangent of negative x is equivalent to negative tangent of x, okay? Negative tangent of x. So that would be my solution there. Okay, example 4, write the trigonometric expression as an algebraic expression, okay? And this one can be a little bit tricky, but we can use our sum identities and difference identities as well for these, okay? So in this one, we're going to use the sum identity for cosine, okay? We're going to call arc sine of 2x is going to be our alpha, okay? And our cosine is going to be our beta, okay? We just need to look at these two kind of reference triangles, okay, in order to write this as an algebraic expression, okay? And since we're defining alpha as arc sine of 2x, okay, if I were to take the, say, inverse sine, or sorry, if I were to take the sine of both sides here, okay, I'm left with this expression, sine of alpha is equal to 2x. Okay, and same thing here. I've got beta is equal to arc cosine of x. Okay, and again, I'll write it out here. If I take the cosine here of both sides, cosine of beta, okay, I'm left with cosine of beta is equal to x. Okay, so now I just need to take a look at my two triangles here, and this green triangle is going to have an acute angle alpha. And this blue triangle is going to have an acute angle beta, okay? So now I've got cosine, let's work with our alpha first, okay? So sine of alpha is equal to 2x, okay? Or I could think of this as 2x over 1, right? Because sine is going to be opposite over hypotenuse, okay? I know my opposite is going to be 2x, and my hypotenuse is going to be equal to 1, okay? So how can I find this base here? Well, I can just use my Pythagorean theorem, and that's going to equal square root of 1 minus 4x squared, okay? 1 minus 4x squared. And similarly here for cosine of beta, okay, that's x, or think of it as x over 1, okay? And cosine is adjacent, okay, so it's going to be this bottom leg here, over hypotenuse. And then I can again use my Pythagorean theorem to figure out that this opposite leg is going to be 1 minus x squared, okay? 1 minus x squared. Okay, so now I've got these triangles solved for all of their legs, okay? So I can just go ahead and have a look. I'm gonna rewrite this as, instead of cosine alpha plus beta, I'm gonna rewrite it as this right hand of my identity, okay? So I'm gonna rewrite this as cosine of arcsine of 2x times cosine of arc cosine of x, okay, minus sine of arc sine of 2x times the sine of arc cosine of x, okay? Okay, but we just solved for we said that, we just said, okay, but we said that our arcsine is equal to alpha, okay, and our arc cosine is equal to beta. So we can go ahead and just kind of keep this as cosine alpha, cosine beta, minus sine alpha, sine beta, okay? So now I understand what is cosine of alpha. Well, cosine of alpha is just going to be this square root of 1 minus 4x squared, okay, over 1, right, over 1. So I'm not going to write in the over 1, okay, but that's over 1 since that's my hypotenuse, okay? And then the cosine of beta is going to be x over 1, okay? So I'm just going to put an x out here in front of my square root, okay? So this term here equates to this right here algebraically, okay? So minus now sine of alpha, again looking at my triangle, sine is opposite over hypotenuse, so that's going to be 2x, okay, times sine of beta, that's again opposite over hypotenuse, so that's going to be root minus x squared, okay? So again, this term here is equal to this term algebraically, okay? So this is going to be my final solution for this problem. All right, let's take a look at one more example. This is kind of a two-part example. Okay, I've got cosine of pi over 2 minus x is equal to sine. We've seen this before. This is our cofunction identity, cofunction ID. And then we also have what's called a reduction identity here. Reduction identity. Okay, and we're just going to use our sum and difference to verify these real quick. Okay, so since this is going to be, think of this as our alpha minus beta. Okay, I can rewrite this as cosine of my alpha, which is pi over 2, again just using our identities, times cosine of my beta, which is x, okay, plus sine of my alpha, pi over 2, sine of beta, which is x. Okay, and I know that the cosine of pi over 2 is 0, and sine of pi over 2 is just 1, okay? So this is going to simplify to sine of x, which is the right-hand side of my equation, so that checks out. Okay, same thing over here. I've got sine of alpha plus beta. Okay, so taking a look back at my sum identity for sine, this is going to be equal to sine of alpha, which is pi over 2, times the cosine of beta, which is x, plus cosine of beta, cosine of alpha, which is pi over 2, times the sine of beta, so sine of x. Okay. Again, sine of pi over 2 is going to be equal to 1, and cosine of pi over 2 is equal to 0, so this whole term drops out, and I'm left with just cosine of x. Okay, so I use that to verify both of my IDs there. Okay, those are all the examples for this lesson, you guys. Good luck with your practice.